Okay, just handed back your finite state machines. They all look pretty good. You might have to make a few adjustments. You'll see that whenever you get into your actually doing your project. And so today, what we're going to do is, again, here and now, what we're doing is we're sort of in parallel. You should be working on your project in the background, or in a concurrently. And at the end of class last time, we introduced these conditional branch instructions. And so what we looked at last time was how to do local variables, which are allocated where?
Runtime stack?
On the runtime stack. And the way you do that was you use stack relative addressing, and you manipulate the stack pointer with add_sp and sub_sp to do the actual pushes and pops. Actually, it's the other way around. Sub_sp to do the push, add_sp to do the pop. Okay, now, and what we didn't quite get to was flow of control. And your homework assignment that's due today is flow of control. Oh. So anyway, what we'll do is let me go over this material first and show you some examples. And then this may clear up some questions that you have. If not, then we'll spend some time at the end of class seeing if there's any questions about the homework assignment that's due tonight at midnight. Okay, so now, here we said that we have 6 conditional branch instructions that deal with less than or equal to, less than, equal to, not equal to, greater than or equal to, and greater than, and then 2 additional instructions that deal with branching on V and C, if there's overflow, and if there's overflow considering assigned, considering the operand to be assigned value, and branch on carry, which considers the operand to be unsigned, or the result to be unsigned. And so what we want to do now is we want to take a look at this program from figure 6.6 that has a simple if statement without an else. Okay? Now, I think what we'll do here is we'll keep this up on the board, and let's see if we can real quick just go through a translation of this. Okay. All right? And so don't peek if you're looking in, no peeking. We'll just try to, and you guys out there too. Okay, so we'll try to. Let's see if we can get this. All right. So what's always the first instruction? Branch. Yeah.
Symbol number.
And you are right. Number. And because it's a local, it's a dot equate. And it equates to 0, because when you push that on the top of the stack, that will be where it is. Okay? And then what? And then we'll branch to main. So here's our main. And the first thing we do is sub_sp is correct. 2. And what addressing mode? Immediate. Because what are we doing? We are. Yes, we are allocating. So remember to put here's another reason you got to not do it on paper. You got to make sure and put your trace tags in there, and then you got to make sure they work.
So
you see them
as Pepe programs.
Oh, absolutely. There is no way I'm going to take this on paper. You'll never hand in programs on paper when you can run them and debug them and make sure they work. Right? So yeah.
I started doing it on paper, and then I tried to put it in the program, and it was completely wrong.
So there's your testimonial.
Yeah.
See, there's a testimonial for those of you who are trying to do this style dry lab. That's like in the lab, you just fill in the blanks. Don't take the data. Okay. Anyway. All right. And so now, okay. Well, yeah, you have to say allocate, and you got to do the trace tags. Pound. Oh, by the way, I guess we need a trace tag for this one too, right?
Local variable.
Yeah, local, and then blah blah blah, and then this would be a pound 2D because it's a integer, right? Mm-hmm. And it's a 2-byte integer. Okay, and the sub_sp, and then this is allocate blah blah blah, and then what goes here? What's the trace tag that goes on this one? No, pound number.
Oh right, okay, pound number.
Yeah. Okay. So yeah.
So now
we need. So now what do we need? We need a input, right? Deci. And what are we inputting?
Number.
Addressing mode.
Stack.
number, stack relative. So decimal input number, stack relative. Then what? Now comes the if.
We have to do
Now
some
we
sort
have
of
to load the
computation.
accumulator.
Yeah, now, how do we do this?
Load
Yes, what we can do here is load accumulator, number,
Yes.
S. Now here's the thing, if you look up load accumulator, maybe you should,
Set all
I don't have
stats
the,
bits.
yeah, I don't have a slide convenient to show. So if you look at the inside front cover of the book, check out which status bits are affected by the load accumulator instruction. Does it say? It says N and Z. Okay, so that sets the N and Z bits. So it will set the N and Z bits depending, and so what will it set? The N bit will be 1 if the number that it loaded was negative, and it will set the Z bit to 1 if it's all zeros. Okay, so now what is the if statement? If number is less than 0. So what would this, so what would we do?
So we want to branch if it's greater than.
So we want to,
Equal to?
yeah. So we have to take the opposite of that test, right? Because if it's not greater than 0, we want to, that's when we want to branch around. Are you with me? So this would be BR what?
GE
BRGE
and
to where? To some place later, so we put a label here. We'll just call it end if. And it, and you know, and it's common practice to leave off the addressing mode because this is like a branch instruction. Okay, so that has a default immediate. Yeah.
so now we do.
So now we actually have to do the number gets hyphen number. Okay, now here's an interesting. Here comes an interesting thing. If I just told you, how would you translate? How would you translate here over here, over here? Over here, if I just told you to translate this, number gets negative number,
We'd have to load the
what would you do? You would do what? You do load accumulate number,
and then negate.
neg, and then store accumulate number, right? If I just asked you to do that. So let's do that. So let's do number. So what did you say? Load accumulate. Load accumulator what?
Number S.
Number, addressing mode, stack relative, yeah? And then what?
Gate.
Neg what?
A.
Neg A. And then store accumulator,
Number.
number S. All right? And then,
And this.
and now this next one, if this branch, if greater than were true, it would want to go to this next one. So here's where our end if is going to be. And
Deso.
this will be deso number, right? Deso number addressing mode,
S.
number S. And then we ignore the return 0. Is that right?
SP.
Oh, you're right. We have to add SP to deallocate.
It's my goal in life.
So add SP, how much?
2.
To immediate.
Yeah.
To deallocate, blah, 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 blah. And then stop, and then dot end. All right? So let's see if we did it right.
Your indentations are in the film.
Sorry, yeah. See, that's why that's another reason you shouldn't do it on paper.
Why?
I know, but anyway. Okay, so did we do it right? Did we do it right?
Yes, we did.
We did? Check that out. Are we good? Okay, now, oh, and here's one more thing. Here's a little picture of how it's structured in figure 6.7a, how it's structured at level HOL6. You indent, you have the brace and you indent, but at level 5, you actually have to do this test with the branch, and then you change the value of the program counter so that the next one won't be the next instruction to execute won't be the one that physically follows it, right? So this little diagram of the difference between an HOL6.
These instructions, will we always use the branch command that's equivalent to what comparison the test does in C++?
So opposite.
Well, with the if statement, it's the opposite.
So we would say branch if greater than.
And why? Yeah, and why is that? Yeah. Because why is that? Because
we're doing
if that's
with-
true, yes. Yeah, because that was a good observation, and that's a general rule for the if statement.
Right.
So so whatever the test is, you do the opposite of it, and then because you branch if the negation of that condition is true. Yeah? Now, you guys, what did we say? What did we say about these three statements? Load accumulator, neg accumulator, store accumulator. What did you notice I could tell you guys wanted to?
The load is
This one is actually what?
repetitive.
Repetitive,
Yeah, this one is superfluous. This is not needed. Why not?
You already loaded it.
Because we already loaded it. Now, remember, what we're doing with all of this translation stuff is we are seeing what a compiler would have to do. Are you with me? So really what happens in real life is the compiler is the one that is making that is generating the code. Now look, let's suppose instead of you doing the translation, suppose you were writing the compiler to do the translation. And the compiler is automating this translation process. Now, which would be harder for you to automate? Would it be,
It's harder to not load it again.
it would be harder to not load it again because you would actually have, the compiler would actually have to go back and figure out if during the execution.
Is that something you can even do? Is that Turing decidable? Like, is that something that's possible?
That is oh boy, I love these questions. The question is that Turing decidable? Yeah, yeah, you're right. That is a very good question. And that's a really great question to ask when you're learning all this stuff about computability. Yeah, what do you think? Just imagine, what do you think? Because wouldn't it have to execute it to, how could it? How could it know that it's in there?
You could check if the...
It would be more work to check if it was in there.
You'd have to check...
It would be. So what I'm saying is, it would be easier to write the compiler to do just always do, when you have something like this, just always do this and not, this will always work.
Yeah.
Right? So the compiler, it would be easy to write the compiler. It would be do you see how difficult it would be to write a compiler to know that? Now what do you think? Do you think a compiler can do that?
Well, isn't it... But typically, the more difficult it is to write, the more efficient it is, right?
Oh, for sure. Let's think of, that's a really good observation. Does everybody understand that by leaving this instruction out, we do not change the meaning of the program. The program still works correctly. So it is correct to leave this out. It is a correct translation.
Right.
And not only is it a correct translation, but what about the program that runs? When you run the program, will it run shorter or longer, or does it the same? It'll run faster. So not only is it less code, fewer instructions in the code, so it takes less storage in memory, it also runs faster because this is not needed. So wouldn't it be great, if it's possible for the compiler to do that, wouldn't it be great if it would do that? So what do you think? Do you think it's possible? Yeah, you asked the question. What do you think? Well, think about what the compiler would have to do.
I think it's possible, but I think it would be more work.
Oh, well, for sure it'd be more work. That's absolutely for sure. But is it possible?
I think so,
I
yeah.
don't think it is.
You don't think it is?
I don't know.
What do you think?
Yeah, let's see.
I don't know.
Yeah, it's possible.
It would have to check the.
What would it have to check? Because what would it have?
If only like it's just running down and whenever it loads something, it has some sort. It stores like that was the last thing I loaded, and then whenever it
Right.
has to load it again, it checks if it's
it-
already loaded it, and then.
So couldn't it keep track of that?
Sure.
It would have to have another, like,
But it could loop. Would it loop forever? Because
Well, now that's a good question, but can it detect if there is a loop?
no, that's the halting problem.
That's the whole thing.
No. But what I'm saying is, if it knows that it's going, could the compiler not say, load accumulator here, and could the compiler not detect that if it ever gets to here, that the accumulator still has this in it?
Yeah, I think so.
Maybe.
Okay, the answer is yes it can, and yes it does.
Yeah, I guess it does.
Except for, that's the difference between what we call an optimizing compiler and a non-optimizing compiler. So here is the principle of an optimizing compiler, okay? What an optimizing compiler does is it eliminates unnecessary instructions in the object code, okay? And now, oh shoot, I have the answer up there. I should not have shown the slide.
Takes longer to compile.
Obviously, what happens is, in order for it to check all that stuff, the compiler, when it's translating, takes longer to run because it has to do all of that logic to figure out what's in the registers. This is register allocation. In fact, the PEP8 only has one accumulator. Most other real CPUs have a whole bank of registers. And so it can schedule, okay, this is a local variable. I'm always going to keep the local variable here, and this one here, and this local variable here. And so it assigns them, and then it keeps track of if is it still there.
Wow.
And it can do that, optimizing compilers. But obviously, optimizing compilers take longer to do what?
compile.
To compile, to translate. On the other hand, the object code that they generate is what?
Much faster.
Faster to run. So now here's my question, which one's better?
You're probably.
Trick question. Which one's better?
Depends
Trick
on what you want.
It depends on what you want,
So
okay?
go back to like the looping part where like 90%, 10% of the program takes 90%
90%
of the
of that,
time.
that's not really related to this question, but yeah.
Say that instead of an if statement, we had a loop,
Ah,
and we left out the load, then every time it loops, it would negate it, and then negate it again, and then negate it again, and we'd end up getting either a positive or a negative at the end, because we
Well,
never set it back to being positive.
yeah, loops are more difficult to analyze, for sure.
But
so-
can it handle them?
It can handle some loops, yes, it can do loop. Listen, compilers have been around so long. They have got this down. It's incredible. I mean, how much progress has been made in the last 20 years. I mean, because it's so important. Because to get back to my original trick question, which is better, optimizing compiler or non-optimizing compiler? Trick question. And what was your answer?
It depends.
It depends. Okay, so now let's think about it depends on what?
If you want better object code
Or faster compile time. So here's my question. When do you want fast compile time?
When you're testing things a lot?
Yeah,
Like when you're compiling.
when do you want?
Works. Like
Yes, when you're doing what to the program?
unit tests.
Yes, when you are writing the program and debugging and writing and debugging and writing and debugging, right? So you have a big program like Microsoft Word. It's a huge program, right? And it has a bazillion different, and to compile that sucker takes, you don't just sit around, you don't just press a button and boom, and all of Microsoft Word is compiled. See what I'm saying?
while to load.
It takes a while, yeah, it would take, so if you're in program development, what do you want? A non-optimizing or an optimizing?
Non-optimizing.
You want non-optimizing because you want fast compiles to get all the bugs out. Are you with me?
Let's get those bugs.
But then, once you get all those bugs out, what do you want to ship to the customer?
The
How
optimized.
faster it is.
Yeah, so then what you do is the compiler normally has options. And you can, and there's lots of different options. All compilers nowadays, they have a ton of different options, and they are optimization options. And it's not just, it's either optimizing or it's not optimizing, it's, do you want to optimize this kind of optimization, or this kind of optimization, or this kind of optimization? And you know, when you're into the, you know, when you're in the industry, and when, you know, you can, there's a whole range of stuff, and when you're developing commercial software, you know what all those optimizations are, and I'm going to turn this optimization on and this optimization off, and blah, 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 blah. But in the end, right before you ship to the customer, what do you want? As what? As optimized as possible, because what does the customer want?
The objects are
Fast. Yeah, he wants his app to execute fast. Now, is that story? That's the story. Okay, now, here's the thing. What are we going to do here? Well, for these programs, in some of these examples, we optimize a little, some we don't. But whenever we get to one, you know, whenever we get to where we have a choice to optimize or not, we can say, well, let's optimize, or well, let's don't optimize. Let's just, you know. So it's for us learning.
We don't miss points on that.
No. But what we should, but as we do these examples, it's a really, really good exercise to know, you know, to see what the optimizations are possible, and to think about what the compiler construction, what the compiler writer has to, how hard it would be to do that particular optimization. That's the way to think about this stuff. Yeah. Did you have a question?
I have a question from a while ago about that, what we wrote on the board. Why don't we, is 0 just default? Because why don't we do CPA 0 to compare it, like do the actual instance?
Yeah, that was another optimization. We haven't done the compare instruction yet, but we could.
But how else does it know that to branch greater than or equal to what?
0 is default.
Because when we loaded number into it, it set the n and the z bits based on what the value of number was.
Right.
But we're comparing
So if
it
value
to
is
0.
positive, then the n and z bits reflect that. If
Yes.
it's negative, it
Okay,
reflects
so
that.
it's only because we're comparing it to 0 that it works.
On the branch.
Yes.
Because in C++,
On the
we're
branch.
asking whether or not number is greater than 0, or less than 0.
How do we know?
Oh, I see what you're saying.
Yeah. There's less.
I see what you, oh, wait. So if we go back to the original, we said if number, oh, right.
So it only
Yes, we
works
had,
if it's 0.
yes. If that were not 0, then we would actually have to do a compare.
Okay.
Oh, I see what you're saying. Yes. Back here on the original program, the only reason this works is because we say if number is less than 0. Okay, question?
Do we always use the compare for these kinds of things, except for like this kind of?
Yeah.
Okay.
We have to.
You
I
have
wrote my whole
to.
program.
You have to.
Loading a character and then subtracting the character I was comparing it to,
But-
and then branching on what
Oh,
it's.
no, actually, okay, whoa. That's really a really good observation. In fact, that brings us to the compare instruction. So instead of subtracting, look what compare does.
It probably does that. Yeah.
It does subtract.
Of course it does.
What it does is it subtracts, but then instead of storing it in the register, what does it store it? It doesn't store
It doesn't
it.
have-
Some temporary
Sets
thing.
these bits.
But the only reason it does the subtract is to set the bits. So that's what compare, the compare is subtract, but without setting the bits.
With setting the bits.
I'm sorry.
Only setting the-
With only setting the, yeah, I'm sorry.
But doesn't subtract only set the? Oh no, because it changes
No.
what the accumulator is.
Yes,
Okay.
yes. Are you with me? Is everybody clear on that? Okay. So with that in mind,
Much easier.
let's do this next one. Now, what is this next one? Is this next one a loop?
No.
If with an L.
Oh, it's if with an else. Oh, okay. Now, do we have, is our variable local?
And we have a constant look.
Yeah. Okay, so let's do this one real quick. Branch to main, right? Okay, so now what?
Limit is a symbol.
So limit dot equate. And now, what is this dot equate? Because it's a constant, this is going to be 100, right? Okay, and now we have our variable num, right? So what is that, num?
Equate 1. No, 0.
Dot equate 0. And this is, blah, 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 what?
Local variable.
Pound 2D? Okay.
First one is also pound to D, isn't it?
Yeah, do we need to say
But
those?
it's
Oh, no, limit doesn't show, no, hold on.
Constant.
Yeah. Constants don't show up in memory,
Okay.
so we don't trace them. They're not traceable. Are you with me?
Yes.
so in, is this a constant? The last thing.
No. That's a local.
Yeah, they don't, because their values are immediate in the operand. Do you see? So there's no place in memory we can go to look at it as far as the memory tracer is concerned. Is that clear?
Yes.
And then now here's main.
How come we can trace num, I realize we're gonna put it on the stack, but
How do we trace what?
why can we trace num? Like, I know we can put it on the stack at some point.
We do put it on the stack right here. We do sub SB 2,
Is it when we do
Immediate.
pound num that it links it up to?
and this is blah, 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 pound num. So when you're actually running the PEP8 program in the trace mode, and when you're in the debug mode, when it does this sub SP, that's when it's allocated, and that's when the stack shows up on the tracer.
Right.
And it's labeled with num, and the format, the value that it's showing in there
Comes to that
comes,
format.
because the assembler sees this num, and this is hooked with this.
Okay. Gotcha.
So let's allocate pound for dot equate 0. Is that
No, this is not, yeah, this is local variable.
local variable?
Local variable, this is allocate. Because see, when you sub SP, that's when you're actually putting it on the stack. It's executing. Are you with me? It happens when this statement executes. Okay, and then what?
Decimal.
Deci num. Addressing mode,
Or S?
S, stack relative, okay.
Then
And then what?
Load accumulator.
Load accumulator,
num,
num, what?
S.
S.
Then CPA.
And now compare accumulator. Yeah, now we do CPA. Now compare accumulator, because it's if num is greater than or equal to limit. So what's the opposite of greater than or equal to?
Less than.
Less than.
We'll do
Wait. So, yeah, sorry. What do we compare? We're comparing it with limit,
immediate.
immediate. Because limit is a constant. And now, what is the opposite of greater than or equal to?
Less.
Less than. So it's BRLT. To where? To else. And then, and sometimes just, it's not necessary, but sometimes I like to put a little if here, even though this label is never, isn't
First
needed.
lift,
Would it be
yeah.
on the?
Oh, sorry.
So you can put the symbol there, but it doesn't really do anything,
It doesn't really do anything.
except tell you that that's where the.
Is this where the if, yeah,
Yeah.
yeah, so sometimes I like to put a little if here, just, yeah, it's just self-documenting, But that's kind of cool, because you can see the C++,
So
Okay, and now,
output,
stro, message, direct, right?
yeah.
Actually, there's going to be more than one message, so let's call it message 1, direct.
So why do we do message here, even though it's not like a variable or anything?
There's a string out.
Well, because that's the address of where your .ASCII is, where those string of characters is
Oh,
going to
well,
be in with the
.ASCII.
.ASCII. Yeah. Well,
Instead of just.
Also, also the .ASCIIs we always put at the bottom, not at the top.
So now we
Oh.
have to branch to end it.
And now it's an unconditional branch, right?
Yeah.
Because if that's true, you do the first and you skip the else. So you have to put the branch to else here.
Or you branch to end it.
No, you branch that.
Sorry.
Because you don't want to do that.
You're right.
Branch to
You
end.
branch to end if. Yeah, you want to branch to end if. And now the else part, now where we branch to this is, now here's where our else begins, right? So else, colon, and then this, and now what is this? Stro,
Now end it.
message to direct. Are you with me?
And if.
Do compilers that do this use symbols?
They can, yeah. Yes, they do.
Well, that could get really.
Yeah, and they have symbol generators, because they have to make sure that they're unique. So they're combinations of letters and numbers, and they'll generate the next symbol. Yeah, in fact, we'll see. I'll show you. We don't have time today, but I'll show you we'll do, in a real one, we'll do a C++ program, and we'll show you the actual code that gets generated for the processor, for this processor that's in here, an Intel. And you'll see how that works. It's cool. I'm telling you guys, the concepts, it's all just like this. You'll see. And now end if. So now what is our end if?
Stop.
Oh, we don't do anything, huh? Stop.
Do we need an inline? Oh no, I guess there's a line.
Nope.
And then we have.
And now we have our messages, right? Message 1, message 2, and .ASCII, .end, right?
Why does we put the .ASCIIs at the end there?
Well, you got to put them somewhere, and you got to put them before the end because the end is.
But I mean, like we make room for variables at the
Yeah. Well, you know, it's because it's kind of like we kind of like to have the style where the variables and the constants are in the same order as in the C++ program.
Oh, okay.
See what I
And then
mean?
we just tag these.
And then you just tag those, yeah.
Oh, we forgot to add SP.
Oh, we forgot to add SP. Shoot, I knew there was something.
What happens if we don't?
Well, yeah, it will.
Well,
Sure.
you had some really good warning messages in Pep 8.
Oh, are you like
I
that?
didn't have my tag
I
fit
thought
and it
it
wouldn't let me.
I had num set to 0 and it was a 2D pound 2D, but then I only did sub 1. And it said warning, like this is you didn't allocate enough memory for this value or whatever.
Yeah.
Okay.
Yeah. I'm glad you like it.
Yeah.
Meaningful error messages. That's what you're going to give. That's what you're going to do on your translator.
Yeah.
That's a big deal. Add SP to immediate, deallocate, blah, 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 pound num, right?
We don't have to do that, right?
Yes.
Cool.
You know,
I did it on my homework.
Yeah. Okay, and then the same we had before, right? Okay, so here, let's see. Drum roll. Did we do it right?
Yes.
Now see all this, aren't you glad I'm not requiring you to do the comments in C++?
I did that helped.
Oh, good. I'm glad you did
How
that.
come they have the branch before the string out?
What? What's different?
No, you don't.
Oh, okay, never mind. We got it.
Are we good?
Yeah.
Did we do that correctly? Oh, we are perfect. Okay, so here is, on this next slide, here is the structure at level HOL6. And here, we had to have that extra branch around the branch. Yeah?
How come they don't branch to the same spot? Oh, one branches to else. Okay, and then
You see how that works?
and then to
Now, can you imagine having to write in assembly language? I can remember the day when applications were written in assembly language.
It's faster compiled.
It's faster to execute too. Because no matter how good an optimizing compiler is, a good human optimizer will outperform an optimizing compiler.
That's so cool.
Because it's very difficult to automate that. Because a human can know, is designing the algorithm and can know. You see what
I
I'm?
feel like higher order languages came out of people trying to do like a shorthand of what they needed to write in assembly code.
Yeah. Well, what's the fundamental question of computer science? What can be automated? So that's what. You're right. That's the point. Okay. So here is our loop, an example with a loop. So let's do this. Let's see if we can do this loop example. Okay. Are you ready? What's the first one?
Global variable.
Oh, global variable. Oh, we still do branch domain. Okay. Yeah. Oh, yeah. You took away my surprise, my thunder. Letter now is global. So we've been doing. Let's go back and do a global example here.
Dot block.
Dot block.
This one.
And now, oh, sorry. It's a letter. Dot block 1. Now, what do we put here for this? We don't.
Pound 1C.
Yeah, this is
Variable.
global variable pound 1C. And now what?
character in.
Name,
main,
Well, main.
carry,
carry,
letter,
letter. But now what's the addressing mode?
No,
direct.
it's direct.
Now it's direct because it's a global. See?
It's been a while.
It's been a while, so let's go back and remember how to do globals versus globals.
Now, start the while.
Now what? Oh,
Now, load accumulator.
oh, and we also didn't have to do sub SP here because it's not no locals.
No.
Okay, so now
So
what?
load accumulator.
Load,
Load byte accumulator.
Oh, yeah. Now, here's the problem. What we had better do is, whenever we do this compare,
Yeah.
it's going to compare the whole thing. It's going to it compares both bytes of the accumulator.
Is that what you have to load?
So can we?
So what you had better do, but load byte only loads the low order byte and leaves the high order byte unchanged.
so load accumulator all 0.
You had better load accumulator to zero it out the high order byte.
Oh.
Are you with me?
So we load.
So load accumulator,
Before the loop.
0,
And then load
immediate, before we get that byte in there.
Now the while loop starts.
And then load byte.
And now what we do is we look, yes, you are right.
While.
So,
Well, that's clever.
wait.
Yeah.
Simple while.
While?
Yes, yeah. Okay, so symbol while, and now what?
Load byte. Accumulator.
Load byte accumulator, what?
Letter.
Letter, direct. And now what do we compare it with?
That's stop.
You want
Star.
Branch equals.
No, we have to compare it first.
Oh yeah, CPA.
So compare accumulator. Now what do we compare it with?
Character
The
star.
character star.
Star,
Immediate.
immediate,
Which is
right?
And should be equal to?
Branch equal.
And then branch if equal to,
The end.
BREQ, to end while,
Is that the convention you want us to use?
sure. And then what?
Character out.
Character out.
Or do we have to load it again?
We're not outputting it from the accumulator, we're outputting it from where it is in memory.
Yeah.
So, Caro what?
Letter.
Letter, direct. Good.
Okay. Carry.
And then,
Alright.
and now,
Carry.
carry,
Letter.
letter, what addressing mode?
Direct.
D, because it's global. And
Additional branch to while.
now you got to go back to the test. Yes. So, unconditional branch to the while. Excellente.
Oh, okay.
Because that takes you back to where the test was. So it's implicit in C++, it's explicit in assembly language.
We don't need
symbol and while.
an end while somewhere?
Oh, you're right, you are
While
right.
stop.
We need the, yeah, because this needs the end while, yeah. I was getting ahead of myself. End while,
Stop and dot it.
stop, and then dot end. So did we do it right?
There we go.
There it is, figure 6.10. Did we do it? Good
job.
deal. Good job. And here's a picture of it in HOL6. Now what you have to do is you got to explicitly have that loop back up there.
That's funny.
Yeah? Now, here's another one.
Great.
Here's another one. I think I'm going to skim through this one. This is the do loop. Now, what's the difference between the do and the
Check the
while? The test is at the bottom.
That's interesting.
So look, so are these local or globals?
Global.
Global. So what will the cop be?
Dot block.
Dot block, how much? 2. The driver will be
Dot block.
dot block 2. Are you with me? Well, branch to main, what will happen?
What's that called? We'll have to load.
Load accumulator 0, store accumulator
25.
cop, load accumulator 40 immediate, top. And now what happens when we get to this do?
It's like opposite.
It just does it.
It just doesn't.
But we'll,
It just
we'll
go.
need to put a symbol.
We'll need to put a do symbol there.
That it can branch back to.
And then it'll do cop,
Now-
it'll do load accumulator 25, add accumulator cop.
But now we want it to branch if less than or equal to.
No.
Sorry, I said load, no, wait.
or less than.
No, I said it wrong, yeah, hold on, before we go on, I made a mistake in what I said. How will we do cop plus gets 25?
Load cop.
Load it.
add
Load accumulator,
Add.
load accumulator what?
Cop.
Cop,
Direct.
direct, add accumulator,
25 immediate.
25 immediate, store accumulator, cop, direct.
Yeah.
Are you with me?
Same for driver.
And then when we get, now what's going to happen when we get to the bottom?
We have to branch if less than, right?
We will,
Greater than or equal.
now it's, oh, wait,
wait.
is this,
If less,
oh, yeah, now, what, because this is while cop is less than driver. So if cop is less than driver is true,
we want to go.
we want to go back up.
So it is less than.
Well, couldn't you do it either way you wanted? For example,
No. Oh, yeah, oh, that's a good question. Here's the way we always want to do it. If it's cop is less than driver, we always want to load accumulator cop, compare accumulator driver.
Right, okay. Go
It's
left
just,
to
it's
right.
less confusing that way. Just do it the way it's, I know there's lots of ways, equivalent ways of doing it.
that's not what I mean.
Oh, sorry.
I'm referring to the order of branching. For example, you could branch back to do based on the comparison.
Yes? What else would you do?
Or you could branch to past it based on the comparison, and then
And then branch, yeah, but why do that when you can do, why branch around a branch?
Well,
Why branch around a
it doesn't
branch?
make a difference.
Well, it does. It's an extra statement that has to execute. It's an extra branch instruction that has to execute when you exit the loop.
It's an efficiency.
Oh, okay, so you just branch back, and if not, then it will just keep going.
You could branch.
Right, because, yeah. Are you with me? So now let's say again what the last test is. Load accumulator what?
Cop.
Cop, direct, compare accumulator,
Driver.
driver, direct,
And then
Branch
branch
if
if
less
less
than.
and branch if less than to do.
Do.
Is that what happened?
Perfect.
Load accumulator, where is it?
I see it. Branch is less than.
Load
That's
accumulator,
wild.
cop, direct, compare accumulator, driver, direct, branch if less than to do.
And then if it doesn't work, then it just keeps going.
Yeah, yes.
That makes sense.
Are we
Rather
good?
than two branches.
And here's this. Right? Now, shoot, I wanted to get to, I think you have, this always happens, I'm sorry this happens so much.
On Monday, I have a
On Monday, you have an exercise to do call by value with global variables. I think what I'm going to do is, I'll let you read about the for loop, but you can tell how the for loop works, right? Can you think about how that works? Here's an example of the for loop, figure 6.14. For j gets 0, j less than 3, j plus plus. What do you have to do?
We can make our own local variable.
Well, it's j.
Yeah.
initialize it.
We just
It's
have to
a-
make sure that we add to it at the end,
Correct.
and then have the same.
And
thing.
And then branch back up to the test.
Yeah.
You add at the end and then branch.
Yeah, how does the for,
It's gonna look like,
You branch back up. if
when
it
we
falls.
learned the for loop, we actually did a while loop that had the I++ at the bottom or whatever.
oh, that's an interesting
It'll look
exercise.
like-
Oh, that's really good. That's a nice way to learn the for.
Yeah, that's how we learned it.
Yeah, that's good. You have to have the incrementing at the bottom and then you branch up to the test at the top. Okay, anyway, we'll go over that tomorrow.
Can I ask a question that's related to the homework?
Oh, you know what? There's so much to do before we get to the call instruction that we are.
We're gonna push back the vote.
Yeah, no. We'll still do it.
We'll have it due Tuesday.
Yeah, can we have it do Tuesday?
Oh yeah, we could have it due Tuesday.
I like it.
I like it.
It's just gonna make my Tuesday.
I'm such a pushover.
Just a nice teacher.
Okay, what was your, wait, you said you had a question about which homework?
In the homework to spec,
Now, what was the homework that was due today?
we have to do an if.
We have
While-
to translate two programs. the
If
same
else,
way
if
we're doing.
else.
Oh, wait a minute, that's all we had to do for today?
Due tonight, it's just two program translation.
Right, oh, so we have done enough to where you can do the homework for tonight.
Tonight.
Yes.
But Monday.
Oh, but Monday, oh no, we should be able to have homework. Well, I already said you could do it. Okay, go ahead. What's your question for
Okay, so
tonight's
when-
homework?
On the if you're testing if it's between two things.
Oh, that's a good question. What, did I have an and or something like that?
It's like if your character is greater than A and less than Z.
All right, let's think about this. Yeah, I haven't done the one with the compound with
I
compound.
didn't know if we had to load it and then
Well, it depends on if it's optimizing or non-optimizing.
Mine's not optimizing, but.
mine is not optimal.
Well, that's fine. I mean, we're not requiring optimization. We're not requiring optimization. In all of these, I will not require
I would lose
optimization.
a lot of points if it was.
No, 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 no. Okay, so let's think about that. If, what was it, like, suppose you say, if, here, let me just make up a nonsense example. If, let's say, alpha is less than beta, if alpha is less than beta and gamma is less than or equal to delta. And then you have a brace, blah, blah, blah. How would you do this?
You would do, since it's an
So,
explain-
now, and let's just suppose that these are, well, they could be locals or globals. It just depends whether you put a D or an S, right?
So you test
So what would you do? So you would load accumulator what?
alpha,
So here's the if. So you would load accumulator alpha, let's just say they're globals. Okay. Load accumulator alpha, and then what?
compare accumulator.
Compare accumulator
beta, direct,
beta. Direct, okay?
then test
Now, I won't write anything else down, but let's think about what you'd have to do.
branch greater than or equal
If this is true, you still have to test this.
right, but if that's false,
If this is false,
Then you-
you have, now what is it called in C++? If this is false, that you don't have to check this, what is that called? You should know this.
Short circuit.
That's short circuit evaluation. So you need to implement short circuit evaluation in a situation like this.
and you just go straight to the end.
So what you, yes, so what you should do
one
is,
test and then branch
this
past
what-
it. then-
and you don't have to do this test.
Yeah.
So that's,
Is there a way to do it otherwise?
well, you could,
Condition is exclusive of both of those and then branch on that.
well, you could have a little local Boolean and set it to true, and then,
How would you do ORs?
that's a good question. Because how does short circuit evaluation work with ORs?
If it's true.
Suppose we say if alpha is less than beta,
so you just branch to
or gamma is less than or equal to delta, then, now how does short circuit evaluation work in this case?
So if the first one's true,
If this one's true, you don't have to check this.
so then you can branch to the.
But what if they're,
So you need to figure that out.
Wait
they're
a
both
second.
false?
Well, yeah, if it's false, then you do have to check this one
The
also.
second one's false.
Then you don't.
Completely.
Then you don't do it.
Okay, so you wouldn't branch after the second one in an OR at all if it were true.
Could you set it up the same way, but just do the opposite test that you would have done for?
You always, the style here, this is a really good one. You need to think, you need to be able to do this on both of these, the short circuit evaluation.
Right.
And let's review it again. What happens is, if this is true, then you don't have to test this. If this one's true, you do the if part.
We don't deal with any ORs in this assignment, right?
No.
But what I'm saying
Right,
is,
yeah.
short circuit, this is how short, you have to implement short circuit evaluation. So if this is true, you don't have to do this test. If this is false, then you have to do this test. Now, once you're doing this test, what happens? If this one is true, what do?
You go into.
You do it.
You just continue.
And but so you branch around if this is false.
Yeah.
But then it's not, it's a different way this time.
That's not too bad.
No, it's not bad at all.
When you compare accumulator, it affects the status bits, right?
Yeah.
Yes.
So you would need to load accumulator.
Yes. That's a good point.
That is regardless of whether it's optimized or not.
Yes. Yeah. It has. Yeah. Optimization can't break the correctness
Okay.
of the program.
That's right.
Oh, it's optimized, but
But it doesn't
it doesn't work. Okay. Good deal. See you next time.